Hello everyone and welcome back to another calculus video. In this video we are going to look at comparison tests, and we're going to look at two different ones. The first one is a comparison test. I like to call this a direct comparison. Our goal is to pick a sequence that we know something about, and I'll call that sequence B sub n. So we're going to get to pick this, and then we'll compare depending on if that sequence is larger than the original or if it's smaller than the original. But the goal is to pick something that you know something about. And then the other one will be a limit comparison test. So let's start with the direct comparison test. Suppose there exists an integer capital N such that 0 is less than or equal to a sub n, which is the original sequence, which is less than or equal to b sub n, which is the sequence that we are picking, for all lowercase n greater than or equal to capital N. If the sum from n equals 1 to infinity of b sub n converges, then the sum from n equals 1 to infinity of a sub n converges. So what's happening here is we're picking a sequence that's larger. So if the larger sequence converges, then it forces that smaller one to converge. Now, if we think this sequence is going to diverge, then our goal is to pick a sequence where these numbers are going to come out smaller than the original sequence. So part 2 of the theorem says, suppose there exists an integer capital N such that a sub n is greater than or equal to b sub n, which is greater than or equal to 0. So we're looking at non-negative values here. For all lowercase n greater than or equal to capital N, if the sum from n equals 1 to infinity of b sub n diverges, so if we pick something that diverges and this sequence is smaller than what's coming out of the original, then it forces the original sequence, which is the sum from n equals 1 to infinity of a sub n, to diverge. So the goal is to pick strategically. So let's look at a few examples. In this first one, part A, we're looking at the sum from n equals 1 to infinity of 1 over n cubed plus 3n plus 1. That looks an awful lot like the sum from n equals 1 to infinity of 1 over n cubed. Right? It's just got some extra terms added here. So that's what I would want to compare to. So I'm going to say compare to this. Okay. I'm choosing something I know something about. This I know converges by the p-series test. Okay, because that exponent is bigger than 1. So it forces that series to converge. Also notice that, and I'll say b sub n here equals 1 over n cubed. A sub n is 1 over n cubed plus 3n plus 1. My b sub n values are going to be larger than my a sub n because that denominator is smaller here than it is for a sub n. So it's meeting the criteria. B sub n's larger. I have a sequence that converges that forces the other one to converge. So we would say, therefore, that original sequence, so the sum from n equals 1 to infinity of 1 over, and that sequence is n cubed plus 3n plus 1, must also converge. Now let's look at part B. Part B is looking at the sum from n equals 1 to infinity of 1 over 2 to the n plus 1. This looks an awful lot like a geometric series. So let's compare it to it. Let's compare to the sum from n equals 1 to infinity of 1 over 2 to the n. And we could rewrite that as a sum from n equals 1 to infinity of 1 over 2 to the n. And this is a convergent geometric series. And we know it's convergent because that ratio is less than 1. So we're comparing to that. So again, I want to know, is B sub n greater than A sub n? So B sub n is 1 over 2 to the n. A sub n is the original, which is 1 over 2 to the n plus 1. And B sub n, because that denominator is smaller than that fraction, is bigger than the fraction that's produced with the A sub n sequence. So I'm comparing to something that's convergent, which means that this sequence, n equals 1 to infinity, of 1 over 2 to the n plus 1, must also converge. Now notice in both of these cases, we could quickly identify what we want to compare to really by stripping off all that extra stuff. The first one was 1 over n cubed plus 3n plus 1. So I've got stuff added to that n cubed in the denominator. If I were just to look at 1 over n cubed, that's my comparison. Same thing with the other one. We have 1 over 2 to the n plus 1. If we get rid of the plus 1 in the denominator, then that shows me what I'm comparing to. That third one is a little bit harder. So we're looking at the sum from n equals 2 to infinity of 1 over ln of n. Okay, the reason they cannot start at 1, ln of 1 is 0, and this would be undefined. It doesn't really matter where I start. What has to happen is that you've got to get past a certain point, and that's what that integer of capital N means, where this is going to be a true statement. Either you're looking at A sub n is less than or equal to B sub n, or A sub n is greater than or equal to B sub n. Now, I don't really know what's going to happen with 1 over the ln of n, so let's create a spreadsheet to kind of figure out, is this going to converge or diverge? So I'm using Excel. So n is starting at 2, so this is going to be equal to 2 plus 1, and then I can just add quite a few terms here. And then I'm going to look at, which changes this to 1 divided by ln of n. So equals 1 divided by ln of n. This column is going to tell me what that term is. So when n is 2, I'm going to get about 1.44. When n is 3, I'm going to get about 0.910. So you can see those numbers are getting smaller. The question is what's happening with the sum. So this third, when n is 3, the partial sum would be equal to this guy plus that one. And we're really just adding up everything. Let's see if that does what I think. No, it's not going to do it. So let's change that formula. So it's going to be equal to that plus that. Actually, I'm just going to take the sum column out. I'm going to do this an easier way. So I'm going to say equals sum of these terms. So the first 17, I get 0.808. Let's expand this to the first 35. So I'm going to 14. You can see how this sum's going to get larger and larger. I think this thing's diverging. If I look at the first 50, I'm at 18. So everything's getting bigger and bigger. To me, it looks like it diverges. So let's see if we can come up with a sequence here. What if we compare it to something we know diverges, like 1 over x, or 1 over n? This is the divergent harmonic series. And in fact, if we wanted to, we could actually start this at 2 instead. Because if it diverges starting at 1, it's still going to diverge if I start at 2. And why would I want to do that? Because the original sequence starts at 2. I'm only leaving off that first term for this guy. So my b sub n here is 1 over n. So if I want to use the divergent part of this direct comparison test, my a sub n, the original sequence, has to be larger than what I chose. So is that true? A sub n is equal to 1 over the ln of n. So let's see. So a sub n is a sub n. I'll just call it a n. And 1 over n, and that's my b n. So this is going to be equal to 1 over 2. So did I pick something that's always smaller? And you can see that I did pick something that's always smaller. This column is always smaller than this column, even if I were to look at the first 40 terms. So I picked a smaller sequence, right? And that smaller sequence diverges, then it forces that larger one to diverge. So we would say since the smaller one n equals 2 to infinity diverges 1 over n, then we could say therefore the sum from n equals 2 to infinity of 1 over ln of n also diverges. And this is by direct comparison test. So it's always good to identify direct comparison test by direct comparison test. So if you suspect divergence, pick something smaller. A sequence that's smaller. If you suspect convergence, you want to pick something that's bigger. So our next test is going to be the limit comparison test. So for a sub n and b sub n, those sequences have to be greater than 0 for all n greater than or equal to 1. We're going to look at limits. If we take the limit as n goes to infinity of a sub n over b sub n, and it equals some number that's not 0, then that means both of these either converge or diverge. If we take the limit as n goes to infinity of a sub n over b sub n, and we get exactly 0, and we know that b sub n converges, then a sub n is going to converge also. If that ratio of the limits goes to infinity and b sub n diverges, then a sub n is going to diverge as well. So let's look at a few examples here. So again, you want to compare to something that you know. If I'm looking at this first series, which is the sum from 1 to infinity of 1 over square root of n plus 1, I'm going to compare it to 1 over square root of n. Compare to sum n equals 1 to infinity of 1 over square root of n. Because I know that I could rewrite that power as 1 over n to the 1/2. And since that power is between 0 and 1, this guy diverges. So it's divergent by the p series. I'm picking something that's divergent. I got to figure out which of these I'm using, whether I'm using part 1 or part 3 of the theorem. So we're going to do the limit as n goes to infinity, and it's going to be a sub n, which is my original, over what I picked, which is 1 over square root of n. So I'm going to do keep, change, flip. Keep that first fraction. Change that division bar to multiplication. And then we're going to flip that second one. So I'm looking at the limit as n goes to infinity of square root of n over square root of n plus 1. And this goes to infinity over infinity. So let's see if we can use one of our tricks from Calc 1. What if we apply L'Hopital's? Limit as n goes to infinity. So this is going to be 1/2 n to the negative 1/2. If I take the derivative of the denominator, I'm going to get the same thing, 1/2 n to the negative 1/2. And that's the limit as n goes to infinity of 1, which is going to be 1, which is a finite number that's not 0. So using part 1 of the theorem, we can conclude both either converge or diverge. So we're going to say, therefore, this sum from 1 to infinity over 1 over square root of n is going to do the same thing as square root of n plus 1. It's going to do the same thing as the series that we picked, which we knew was divergent. So diverges by limit comparison test, and I'll abbreviate that LCT. Let's look at number 2. So we're going to compare this. We're going to strip away all those numbers. Let's compare to the sum from n equals 1 to infinity, or all those extra pieces of 2 over 3 to the n. So I'm looking at the series from n equals 1 to infinity of 2 to the n plus 1 all over 3 to the n. And if I were to think about getting rid of that plus 1 so I can find something to compare it to, I can compare it to 2/3 to the n. That we know is a geometric series, and that geometric series converges. Convergent geoseries. So let's use our limit comparison. We're going to take the limit as n goes to infinity. I'm going to use that original sequence, 2 to the n plus 1 over 3 sub n, and I'm dividing it by 2 to the n over 3 to the n. I'm going to do keep, change, flip. So keep that first fraction, change it to multiplication, flip the second. You can see how those are going to cancel. So I'm looking at the limit as n goes to infinity of 2 to the n plus 1 over 2 to the n. So right now I'm in the form of infinity over infinity. So we could apply L'Hopital's again. If I take the derivative of 2 to a power, so like 2 to the x or 2 to the u, it's going to be 2 to the u times the ln of 2. Bottom is going to be the same thing, 2 to the u, which is n ln of 2. So this is going to be the limit as n goes to infinity of 1 over 1, and that's just going to go to 1, and that is not 0, which means that both of these sequences do the same thing. They either both converge or both diverge. Since the first one converges, the second one's going to converge. The original is going to converge also. So we're going to say, therefore, the series from n equals 1 to infinity of 2 to the n plus 1 over 3 to the n converges by limit comparison test, LCT. And then let's look at that last one. Part C is looking at the sum from n equals 1 to infinity of ln of n over n squared. Now in this case, 1's okay, because when I plug in 1, I'm going to get the ln of 1, which is 0, over 1 squared. And 0 divided by 1 is going to be 1. So I'm going to write this down here just so I have it instead of having to scroll up on my tablet. So let's see, what are we going to compare to? What if we compare it to 1 over n, which we know is a divergent p-series. So we're going to take the limit as n goes to infinity. It's going to be the ln of n over n squared divided by 1 over n squared. So I'm looking at the limit as n goes to infinity of the ln of n over n squared times, oops, I'm comparing to 1 over n over 1. So I'm going to have the ln of n over n, which is infinity over infinity, which means we got to use L'Hopital's. So equals the limit as n goes to infinity. So that's 1 over n over n. Just kidding. Derivative of n, which is 1. And then as n gets larger and larger, that fraction is heading to 0. So we tried to compare with 1 over n, we got 0. It was theorem. So if that limit is 0 and we pick something that converges, then it would converge. But we didn't pick something that converges, we picked something that diverges. So this isn't really going to help us with this problem. Let's compare to something different. Let's compare to 1 over n squared. So you have to think about what does the answer mean in terms of the theorem. And in this case, that theorem tells us we picked the wrong thing to pick too. So I'm going to insert a page here. So let's try comparing to the sum from n equals 1 to infinity of 1 over n squared, which we know is a convergent p-series. Now, we don't really know what's happening with the original sequence, so you just try something. You see if you compare to something that's divergent, see if it works. If not, because the theorem's not satisfied, try comparing it to a series that converges. So we're going to do our limit comparison test again. Limit as n goes to infinity is going to be the ln of n over n squared divided by 1 over n squared. I'm going to do keep change flip. And we're going to see those n squareds cancel. So we're looking at the limit as n goes to infinity of the ln of n, which is going to infinity. So that's heading to infinity. This diverges. So let's see what our theorem says about diverging. So part 3 says if the limit as n goes to infinity of a sub n over b sub n goes to infinity, then if we pick something that diverges, then the other one's going to diverge. So that doesn't really help us either because we picked something that converges and we ended up with a part of the theorem that's talking about divergence only. So maybe the answer lives somewhere between 1 over n and 1 over n squared. So let's compare to the sum from n equals 1 to infinity of 1 over n to the 3 halves. So since that power is bigger than 1, this is still a convergent p-series. But maybe we'll get a limit something that deals with convergence. We need something for really part 2 or part 1 of the theorem. We either need to get that limit to be 0 or to be some finite number. That's not 0. So we're going to take the limit as n goes to infinity of the ln of n over n squared divided by 1 over n to the 3 halves. So we're taking the limit as n goes to infinity. This is the ln of n over n squared. We're going to do keep change flip. So now this is going to be multiplied by n to the 3 halves over 1. So I'm looking at the limit as n goes to infinity. This is going to be the ln of n over n to the 1 half. And I'm going to get infinity over infinity here. So let's use L'Hopital's. The derivative of the top is 1 over n. The derivative of the bottom is 1 half n to the negative 1 half. I'm going to clean this up. The limit as n goes to infinity of 1 over n divided by, so let's write it this way, divided by 1 over 2 square root of n. And when I divide fractions, I keep change flip. So 1 over n times 2 square root of n over n. And then when I clean this up, oh, just kidding, this is 2 square root of n over 1. I'm going to have 1 over n times 2 square root of n over 1. So the limit as n goes to infinity of 2 over square root of n. And this guy is going to head to 0. So let's see what our theorem says about 0. So if that limit of the ratio of the sequences goes to 0, and what we picked converges, then it forces the other one to converge. So it took us a little trial and error to get there, but we finally got there, and we can conclude that that sum from n equals 1 to infinity of ln of n over n squared converges by the limit comparison test. So the tests work. The key is picking something that's easy to compare to. Things that are easy to compare to would be power series and geometric series. Easy series to compare to. Power series. And geometric series.